Hello everybody, I hope you all have been doing well. In this video, I am breaking down the method of mathematical induction with the help of this example in the most simple and easy way possible. Mathematical induction is basically used to prove the statements. Keep that in mind that the statements to be proved are only for positive integers, and mathematical induction consists of only two steps. Before explaining the two steps, let's call our statement S of n. Now, the first step is called basis step, which is super simple. In this step, we just need to replace n by 1 in the statement and see if it is true or false. Obviously, if it is true, we proceed, and if it is false, we say that this statement is not true. Now, the second step is called inductive step, which is a bit tricky. So in the inductive step, we consider S of k to be true, where k is any positive integer, and then we prove the statement for S of k plus 1, which I will show you in this video how to do that. If we prove both of these statements true, we conclude that the statement S of n is true for every positive integer n. This definition will be more clear to you when I explain an example to you. Let's take this example for instance. That is a series of natural numbers from 1 to n, and we have to prove that it is equal to n into n plus 1 whole divided by 2. First of all, let's call our statement S of n to start the procedure. Starting with the basis step, which is the first step. According to the definition, we put n equals to 1 in the statement, which I have here in the purple box. When we have series like this, we only put n equals to 1 in the nth term of the series like this, which gave us 1 after simplification. Now we can see that 1 is the first term in the series, so for n equals to 1, we got the first term of the series, which is correct. This implies that the basis step is true, and hence we can proceed to the inductive step of mathematical induction. In the inductive step, we basically take the statement S of k and make it exactly like S of k plus 1 to prove that S of k plus 1 is also true. So what we do is we replace n by k in the statement and assume that the statement S of k is true. After that, we put n equals to k plus 1 in the statement and keep it aside. You must be wondering why we put n equals to k plus 1. We have to prove the statement for n equals to k plus 1. Then why did we do that? The reason being, my friend, is we use this S of k plus 1 statement to find out what we need to do with the statement S of k to make it exactly like S of k plus 1. Here we can see that the statement S of k plus 1 has one more term than S of k, and that is k plus 1. Right there. This particular part is different for every other statement you will be given to prove. So do as much practice as you can, and also watch my new series of mathematical induction where I will explain you how to prove other equations as well as inequalities. Okay, back to the topic. As I'm saying, there is one more term in S of k plus 1, which is k plus 1. So we are adding k plus 1 on both sides of a statement 1 to get this. We also have the statement 2 in the purple box here to get the hint that what should be our next step. as we want to convert the statement S of k into S of k plus 1. Okay. Now we take the LCM of the right hand side of this statement, and we can see that k plus 1 is being multiplied in the statement too. So we take k plus 1 common from right hand side to obtain this. Okay, now we can see that the statement 2 has k plus 1 and we have 2 here, k plus 2. So we split this 2 into 1 plus 1 like that. And voila, adding just these parentheses and it looks exactly like S of k plus 1. The goal is achieved here, people. And this implies that this statement is also true, and we have concluded that S of n is true for all positive integers. That's it for the video. Hope you all learned something from today's video. Please subscribe to my channel and hit the notification bell to be notified every time we upload. Have a great day.